Greetings, Mr. Kolazar's class. For part 2 of our video, what we're looking at is the idea of light and its interaction with matter. Now, the electrons is what we're studying and looking into, and what we've said so far is electromagnetic radiation, or our waves that we've been looking at as they move up and down. What we're looking at is they all travel at the same speed. And that constant speed, our equation for the electromagnetic radiation C, is going to be equal to lambda times nu. Now remember, they're inversely related. As one would increase, the other one would decrease, so that it would stay equal to C, the speed of light. Now, our equation, speed of light is equal to lambda times nu, as our beginning part. Lambda, our frequency in meters, frequency per seconds, and the speed of light 3 times 10 to the 8th meters per second. So as we combine these two units, meters over seconds, we end up with meters per second. Now, as wavelength increases, frequency would decrease, or as wavelength decreases, frequency would increase in order to keep our constant speed of light. Now, our first equation was written in the box, but we could rewrite it if we want to solve for lambda. Lambda then, we would have C over nu, the frequency. So please write this equation down so that we can use that in the future. Or if we wanted to solve for nu rearranged, we would have C over lambda. So whatever part we're solving for, we'd put the other variable under the C. Under the C. Now, all electromagnetic radiation travels at 3.0 times 10 to the 8th meters per second in a vacuum, meaning if there's no resistance in space. So just as a reminder, if one part increases, the other part decreases in order to keep the speed. This part's not part of our notes, but just to kind of show how fast that is, if we were to take from meters per second to convert to miles per hour, that's about 671 million miles per hour, or about 4 times around the world in 1 second. So speed of light, very fast. The key is all electromagnetic radiation travels at the same speed. So just reminding us back from last section, wavelength, one full wave. So the top one, a shorter wavelength versus a longer wavelength. In the same amount of time, they travel the same amount of distance, but as we're going, the frequency would change. So a shorter wavelength, like the top one, you'd get more frequencies. The longer wavelength, like the bottom one, less frequencies of travel. So just as a reminder, as they would travel 1, 2, 3, 1 second, we'd have a different amount of wavelengths, or number of waves per second, depending on that wavelength. So a couple of problems we're going to work through. So inverse, one goes up, the other one goes down. So our calculations for today. What we're looking at is question 11, radio waves are used to transmit information on various channels. Calculate the wavelength of a radio wave that has a frequency of 5.4 times 10 to the 10th hertz. Now remember, hertz unit is a number per second, or we could also write that per second is what that hertz unit is. And what we're looking to solve for is wavelength. So our original equation that we're starting with, C was equal to lambda times nu. We're solving for wavelength, so we're going to rearrange the equation. Always need to start by showing our equation. The wavelength is going to be equal to the speed of light divided by the frequency. So as we're going to solve, the speed of light, 3.0 meters, 3.0, we'll do this right, 3.0 times 10 to the 8th meters per second divided by 5.4 times 10 to the 10th hertz, or I'm going to write it as per seconds. Now right away, our units that cancel out, the per second on the bottom will cancel the per second on the top, leaving us with the meter unit. That's what we're looking for in a wavelength. And then if we wanted to actually calculate this out, if you have your calculator with you, if you have a graphing calculator, we could type this out, and we would start with 3.0, and either scientific or graphing calculator, remember we're going to use our EE key, 3.0 times 10 to the 8th divided by 5.4. Second EE key again, so we don't have to use those parentheses, to the 10th. And we get an answer. As you type in, make sure you get the same answer. We should end up with about 0.0055, and our units meters. So we'll compare the answer from this problem to our next problem as we're going. So solving for wavelength in our first problem, our answer is in a wavelength unit meters. Our second problem, microwaves are used to heat water which cooks food in a microwave. Calculate the frequency of a microwave that has a wavelength of 3.0 times 10 to the negative second meters. So in this problem, we're given wavelength and we're solving for frequency. So calculate the frequency is what we're looking to solve for. And we know the wavelength of the object. Now, C is going to be equal to lambda times nu. And this time we're solving for frequency. So to rearrange the equation, we're going to put lambda under the C. So speed of light, 3.00 times 10 to the 8th meters per second over the wavelength, 3.00 times 10 to the negative 2 meters. Now right away, before we do our calculations, our units meters will cancel meters, leaving us with divided by seconds or per seconds. So now for our calculation part, there it is. We're going to start out 3.0 times 10 to the 8th, EE8, divided by 3.0 times 10 to the negative second. Now this time when we calculate out, notice a lot of times your calculator 1 times 10 or 1e to the 10th if you have a scientific or a graphing calculator. So as we're looking, we're going to write that out as 1 times 10 to the 10th. And then our units are going to be either per second, or let's make this look a little bit better, 1 per second, negative 1, or 1 times 10 to the 10th, and you could say per seconds, or 1 times 10 to the 10th hertz. All three of these are the same answer, so any one of the three would be acceptable as we're going forward. Per seconds, or per seconds, 1 times 10 to the 10th, meaning how many cycles of this would be per second. Now if you looked at these two problems, I think before, make sure you change so yours says 11 and 12 for a little autocorrect to fix up there. If you were to look at those two problems, wavelength, if you were to compare the wavelength of each one, we have a larger wavelength in the first one versus the second one. And if you looked at the frequency answer, it's a smaller answer in 11 and a little bit larger answer in 12. And again, our idea between these two is when you compare your answers to them, wavelength and frequency, we need to remember, are inverse from one another. As one goes up, the other part goes down. As one goes down, the other one goes up, because we need to keep it equal to C, which remember is that 3.0 times 10 to the 8th meters per second, which is the constant speed of light or all electromagnetic radiation. You can begin working on your problems after you've finished up the video, and we will discuss later.